All right. Hello, everyone. Welcome back. Week 6, Lecture 2, Math 154. You already know what it is. So let's take a few minutes and talk about what's on our whiteboard. One of those details might be a small surprise after something I said last class, but when I was planning things out last time, I wasn't thinking about the fact that this is summer. So I was thinking it was going to be a little longer to our midterm. So we are actually going to finish chapter 4 today. I had it in my head that it was going to be the class after, which is why I had said the 12th and 13th. So I wish I hadn't said that because I had originally planned on having the midterm a week after, which would have put us having the midterm for, what is that, the 8th and 9th of July. But because I had said it was likely going to be the week after that, I didn't really feel like I could put the pressure on that quickly. So the compromise is I'm just shifting it up one day for that span that I'd originally said, instead of making you take it 5 days earlier. So I am going to jump down to this highlighted section to talk about it first. Our midterm dates, where you're going to take it at your quote leisure at any point in that 48-hour span on my math lab, will be Sunday the 11th and Monday the 12th. So if you can't take it on Sunday, then you've got all of Monday. It's going to cover chapters 1 through 4. We're going to keep it at 20 questions instead of 25 questions. You will have the full 2-hour period. This is a no notes, no books, but a calculator is allowed. So no notes, no books, calculator's okay. You can use the formula sheet that's provided in Canvas. It is not going to feel like very much of a formula sheet. There's only 2 or 3 formulas in there. And when I say formulas, they're conversion formulas. So you're not going to see anything having to do with calculating interests or future values or grades or weighted averages or any of the formulas and little things that we've seen over the course of the semester, because most of those have just been, hey, multiply these 2 things or add these 2 things or subtract these 2 things, something like that. So I don't really call those formulas in the great span of everything. They're concepts like we talked about. But you do still have to have your time conversions memorized. You have to know how many hours are in a day, how many days are in a year, all of those good things, seconds in a minute, etc. But anything having to do with converting miles to feet or meters to feet or any kind of volume conversion, whatever is needed for the test would be provided in the formula sheet, which again is in Canvas. Please remember there is a very, very, very good review in Canvas that is all encompassing. It's about 55 questions. There is one question that I point out to skip for reasons, but I had to include the first part of that question. It's just the second part is above our pay grade, so to say. But there are no questions in my math lab with just the first part and not the second part, so that's why that happened that way. So if I chose a problem of that format for the test, I would automatically go back and give everybody credit for the second part. That wouldn't be an issue. So midterm dates, we know them. We're going to be prepared. We're going to use the review to study for. The review is not graded, so you don't have to do it, but I suggest that everyone do it. It will be in your best interest. Once again, the questions on the test will be very similar to the ones on the review, but obviously only 20 questions, not 55. So it'll give you an idea of what to focus on. So I'm trying to think of how to describe this. Maybe on the review, there isn't a question about calculating a weighted average. There is, but I'm just saying maybe there wasn't, which would mean that you wouldn't expect it on the test. So the review will help you know what to not focus on. All right, so the other assignments that we have up and coming, 3.4 today, 4.1 and 4.2 next class, 4.3 and 4.4 will be due on the 8th, which is a week from today. Your Excel budget is going to be due on the 6th. The discussion board that we gave last time in Canvas, that's going to be due on the 6th. And then that percent quiz is due on the 6th. I'm already getting emails about this. Just as I said for the pay attention quiz, please make sure that you pay attention to the instructions so you can get your full grade without having to shoot me an email. The review I will have posted today. For some reason, I thought I had already set that up in Canvas. I will double check this evening, and I will make sure that it's up no later than 8 or 9 o'clock when all my classes are done. Sorry, I'm thinking for a second. There was one more thing I wanted to say. We are going to have quizzes pretty regularly for the rest of the semester. There might be 1 or 2 times where I give them back to back, but we still have about 4 more quizzes that I want to knock out, 4 to 5. And well, 4 since we have 4 weeks. And we still have about 4 Excel files left as well. So don't forget about that project. Keep working on that every day. Every day you have an expense, go ahead and add that to your Excel spreadsheet. Remember, you can actually set up all your formulas and your formatting and your charts whenever you're ready. It doesn't have to be the very last day, because remember, the project is due 1 day after the month span of your budget itself. And remember that this Excel file is a completely different budget, has nothing to do with your personal expenses. This is a regular homework with just fill in the blanks and all that stuff, whereas the project will be hand graded by me. Man, I know I had one more thing I wanted to say and I can't remember it. I'll think about it and I'll do it during the whiteboard at the end. But besides that, we're going to pick up where we left off with that guided activity, talking about the income do's and don'ts. So let's get into that.
Income dose is what it looks like to me. Income dose. Use the Census Bureau report Income and Poverty from the previous guided activity, showing income in 2017 dollars for households. So again, we're going to use this table again, so I'm going to have to come back to this. It's kind of tedious, I know, but we'll deal with it. And this one's going to be a little different. They say, compute the total and percent difference in the number of family and non-family households in 2017. Do this in 2 ways, switching the order. Do this in 2 ways, switching the order in the arrow diagram. So this is something I alluded to last class, 5 days ago. I know it feels like forever ago. In that, generally, total change and percent change, it's all based on old and new, original and new, however you like to say that. Whatever happened first, whatever happened second. So new minus old, the second thing minus the first thing. However, we don't have to be talking about total and percent changes with things related to time. We can talk about total and percent change with things not related to time. We can compare apples to bananas. We can compare apples to oranges. Those have nothing to do with time. So saying which thing occurred first and which thing occurred second doesn't really have a sense to it. You just have to have a reason to call the bananas the quote first, or the oranges the quote first, or the apples quote first, or whatever. So in other words, you're thinking about one thing in comparison to another thing where you want the percent change to be based on what you typically are dealing with. So if your store is typically dealing with apples and now all of a sudden you start going and selling oranges, maybe you do the percent change relative to the apples. Or maybe you wanted, you're just always selling apples and oranges, and maybe you want to see what's the percent change relative to apples, what's the percent change relative to oranges, whichever one sounds more awesome. Use that number to give to the media to spin your story, because we've talked about how we can do this last class. So that's what this is relating to. There's no real order of first and second. So one time we're going to call the family our quote original, our quote the thing that we're comparing to. And then one time we'll call the non-family the original, the thing we're comparing to. And we'll see how these total changes and percent changes are affected. And we've really already done one of these, but I wanted to make sure we did this one too. So if you go back to your table, the family and the non-family numbers for 2017. Family and non-family numbers for 2017. So we're not using 2016 at all. We're not using any of these columns. We're just using 2017, and we're comparing family and non-family. So family households, 83,000. See, I'm not just using the married, I'm not just using the female leader, I'm not just using the male leader, I'm using all of them, all the family numbers. So that's the 83,000 number. And then the non-family, see the types of households, you have family-based or non-family-based. So the family-based is all the 83,000. The non-family is this 44,498. Again, I don't care if it's female or male leading the charge. If you add those up, you get this 44,498. Same thing here. If you add the female led and the male led to get the married. I'm sorry, if you added all of these. Yeah, there we go. all three of these. You get its number because it's female-led, male-led, and just married. Okay. So we're comparing the 83,088 to the, where'd it go? 44,000 something. 44,498. So they do this two ways. The first way they ask us to do this with the family being the old. So the family number, let me see if I can get this on the screen all at once. Perfect. So the family number was the 83,088. Now remember, this is really in thousands. There's really 3 more zeros after all that, but we don't have to write it. The non-family number, that was the 44,498. I had to write those down. So that's what we're calling original and new. Again, it doesn't really make sense to call them original and new because the family didn't happen first and the non-family happened second. This is just us saying we're going to be scaling everything to the family numbers. So the total change is the difference of these. That's the 44,498 minus the 83,088. And when you do that subtraction, you should get negative 38,590, right? Yes. So that's a negative total change. That means if we say the family is our starting value and the non-family is the ending value, that says we're seeing a decrease of 38,000 thousands, or negative, or 38 million really. The percent change, so this is where we take the total change, which was the negative 38,590, and we scale it to the original. So we divide it by the 83,000 number. It's going to be a negative number. So negative 38,590 divided by 83,088. And we get negative 46.444. Oh, I forgot to put my 0 there, but negative 0.46444. We have to convert this. So that would be negative, that decimal going right twice makes it negative 46.444. Let's just round this to 2 decimal places like last time, so negative 46.44. And that's a percent now. So that says if you think of the family as the base value, the non-family is 46.5% less than the family as a change. So let's hold on to those numbers. Now let's do everything we just did, but flip the script. Now the old's the new. So now we're saying non-family is the base value, which is the 44,498. The family is the new value, so to say, 83,088. So the total change is the subtraction of those, 83088 minus 44498. Now this will be a positive value, and that's 38,590. We're just subtracting in the opposite order, so the value doesn't really change except in sign. So that says there was an increase. Last time it was a decrease, this time there's an increase. Then the percent change, we take the total change and we divide it by the original. So the 38,590 divided by the 44,498. 38590 divided by 44498. And we get 0.86, etc. 722,998, blah, 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 blah. Converting this, which you can barely see that says convert, sorry. You'll end up with 86.72 to blah, blah, blah percent, which rounded to 2 decimals is 86.72. That's a 7%. And that's an increase. So the whole point of this, when there's no sense of time, is if you are trying to have a more extravagant number, if you're the person running these statistics and you're about to make your news article or give something to your boss, which one should you hand out? Which one should you give out? Do you want to talk about something as a negative change and a smaller value in absolute for the percent? Or do you want to have it be a positive change and end up being a larger value? Which one of these is more favorable to what data you're trying to convey? And a lot of the times it's which one sounds scarier. It doesn't have to be. In some cases, if you're trying to convince some people to buy your product, you want the thing that's less scary. So that would be the opposite scenario. So if a 46% change in 46% decrease in change is scary, and you want to have a positive result, then you demonstrate this one, or vice versa. But it's so fascinating because the total changes are really the same number, just opposite sign, 38,590, 38,590. One's positive, one's negative, because the total change is just a difference. But when you scale something to the original, the size of the original matters. When the original is bigger, it makes the percent change feel smaller. When the original is smaller, it makes the percent change feel bigger. Now, I'm going to have to erase those numbers and everything to answer number 2, to make a sentence out of both of these, a sentence out of beef. So the numbers I'm going to be stealing are the 46.44 in negative and the 86.72 in positive. Okay, so let's clear our screen. Let's take off annotate. Let's throw our calculator down. There we go. Use both of the percent changes from number 1 in sentences. Annotate, and we're going to type for this one. There we go. Okay. So it would be something like this. The number of non-family households 2017 was 46.4% less than the number of family households. That would be from the first one, when we had family as the original and non-family as the quote new. So we were comparing the non-family to the family. The family was the base value, which is why we say the number of the new thing was the percent change, more or less, in this case less, than the original, the base. So the number of non-family households was about 50% less than the number of family households. But when you flip the family and non-family order, so this is the second version, the number of family households in 2017 was, and this was the 80% number, 86.7, and that was 46.44, excuse me, is what we originally had. The number of family households in 2017 was 86.72% more than the number of non-family households. And we're going to skip number 3. So the number of non-family households was about 50, I'm just rounding to simpler numbers, was about 50% less than the number of family households. Or you could say the number of family households was about 90% more than the number of non-family households. Again, what information do you think you want to convey? What's your scenario? And of course, we have no relationship with these numbers personally. It's, are we someone trying to say, oh man, the number of family households is so much better or so much worse? What is the message we are trying to convey? Are we trying to scare people, or are we trying to make people feel good? I think that if you want a positive approach of this, you would probably go with this one. The number of family households was about 90% more than the number of non-family, because in traditional sense, family is good. Family means that we have a good structure at home, hopefully, and we're reproducing and we're going to build our world and things like that. Or maybe you're trying to say something negative, so then maybe you go with this one. Again, that's how this relates to the real world. So when you, a quantitative reasoning student, go and read something like this in the paper, and they say, oh, the number of family versus non-family is this percent change, you can go, okay, well, if I flip the script on this, that number would probably not be as extravagant, and it would be in the opposite direction. All right. So we're still in 4.3. Now we're going to get to the new stuff. All of this right here, but let's just take this one step at a time. Let's just focus here. This is super important. Growth and decay rates in conjunction with growth and decay factors. Now, we have dealt with growth and decay rates in here already. When we've said that your money grows 7% annually, that's a growth rate. If I said that you lose 7% annually because you're paying interest or something, that would be a decay rate. Growth means it's going up, decay means it's going down. So your growth or decay rate is given to you as a percent. So when I say X, I'm just saying something like 7%, 13%, or negative 7%, or negative 13%, again, depending if we're going up or down. When we invest our money, it's going up, so positive 7%. If we lose money, it's going down. Now, when we lose money, we generally don't even think about it that way because we think in absolutes, but we will deal with decays in a more traditional sense. You have got to understand the difference between these two things. And this is something that I always have to hammer out and hammer out and hammer out to my students. We are going to see this in chapter 5. We're going to see this in chapter 6. We're going to see this in chapter 8. We're going to see this in chapter 9. Just like when we introduced proportions in chapter 2, it never really went away. Now I'm introducing something else that's super important that's never going to go away. Most of the things that we teach in QR don't really go away. That's what I like about this course. It's not like an algebra course where we, teach you this thing and then we never use it again. Then we teach you that thing and we never use it again until you get to a pre-calc course. All of this we continue to build on. That's what's amazing about this. So a growth or decay rate, is going to be, this is going to be given you as a percentage. It could be written as a fraction. Rates are fractions, but fractions are percents. They're all the same thing, just represented differently. The word factor means multiplier. The word factor means multiplier. The word factor means multiplier. I actually need to just add that into these notes permanently because I think that's important. Write that down. If I write something down, you should be writing it down. Honestly, if I say something, you should try and write it down too, but I know that can be tough. The growth or decay rate is just your basic percentage. We're increasing 7% a year. We're increasing 9% a year. The growth or decay factor, and it's only one, it can't be both. The growth or decay factor is what you multiply something by to get the new thing. This concept is phenomenal, and we've already used it. We have used this in the past, believe it or not. So if you're given an original value, so say we have 300 of something, and it's growing at 7% per year, that would mean we have the original and the growth factor. That's all you need in order to calculate the new value. You need the old and the growth factor to calculate the new. See, this is a different perspective. What we were doing in the past was we were given the original and the new, the old and the new, and we were finding the percent change. The percent change is the growth factor. Percent change is the growth factor or decay factor. So now instead of being given the new and the old and finding the total change and percent change, now we're going to have the percent change and the original and find the new. Or we can be given the new and the growth factor and find the old. We'll get into that as well. So the growth factor is just you take 1 and you add the percent value, but as a decimal. I know this says 1 plus or minus X percent, but this should be as a decimal. So if you are talking about a 7% increase, the decimal value would be 0.07. So you'd be taking 1 plus 0.07. If you're talking about a 7% decrease, you'd be doing 1 minus 0.07. See, that plus or minus tells you whether you're going up or down. If it's an increase, you choose the plus. If it's a decrease, you choose the minus. So the new is just the original times the growth factor. That's what this says right here. The new is equal to the original times 1 plus or minus that percentage, but as a decimal. Again, this should be as a decimal. Remind you here, I say it twice. New equals original or old times this parentheses right here is just the growth factor or the decay factor. There's no crazy formulas here. There's no negative b plus or minus square root of b squared minus 4ac all over 2a. It's not a quadratic formula. It's just a sum or difference and a product. These are simple ideas, but you have to remember how to use them. We do not give you these as formulas for your test. You have to know them. And again, you add if it's growth, you subtract if it's decay. Now, I did say in general, you're given the old and the growth rate, and then you can do this, but I also mentioned down here that you could be given the new or the original and be asked to solve for either. Don't worry, we'll see that. I might save one of these for the guided worksheets. I'm thinking about that right now, but we're going to do a few more examples that were not in your guided worksheets, the actual official guided worksheets. But you should have seen them if you're looking at your notes to share. All right, so let's try this out. Your old salary in 2018 was $55,000. Not too bad. You know, nothing crazy in this world, but you're definitely able to afford your house and everything, unless you just have extravagant taste. Then your boss gives you a 7% COLA, not Pepsi Cola or Coca-Cola, not a soda. That means cost of living adjustment. Cost of living adjustment. COLA has everything to do with inflation. So on average, our money inflates about 2% a year. We're in a volatile market right now with everything going on. So, you know, maybe that's going to be smaller, maybe it's going to be larger. We could potentially see, instead of inflation, we could see deflation. We're not sure yet. We're still kind of surviving everything right now. But your boss gives you a 7% COLA and attaboy pay raise. Attaboy, this is just me having fun. What's attaboy sound like? Good job. You did good, so we're going to give you more money for doing a good job. If you're a state employee, you'll, well, I should say if you're a state teacher, you'll never see one of those in your life. We usually just get COLAs, but not complaining. And we usually don't even get those every other year. But again, is what it is, not the point of the problem. So this is a pretty hefty raise. So you probably got 2% for cost of living and then 5% for doing a really good job. Maybe you're in sales and you're just killing sales constantly. So your boss recognizes that and gives you a good pay raise. So on top of your normal 2% this year, you get that extra 5, bringing you to 7. What is your new salary? Man or woman, I just like to say man, dude, whatever. If this isn't relative to your life, I don't know what is. Okay, sometimes your boss will say, I'm going to give you a 50-cent raise, or I'm going to give you a $1 raise. Now, when they say it that way, that's kind of a weak statement. They should be saying a 50-cent per hour or a $1 per hour raise, because that's a rate. Just saying you get a 50-cent raise means if you made $55,000 last year, that means this year you make $55,000.50. So hopefully it's a 50-cent per hour raise. But instead of giving you as an hourly rate, I've given it as a percentage of your base salary. So what we need to do is find what the growth factor is. We have the growth rate. Let me give myself some space. The growth rate is the 7%, which as a decimal is 0.07. Meaning that the growth factor, remember, factor means this is what you multiply with, is just 1 plus the rate as a decimal. So 1 plus 0.07 is 1.07. So that says if we want to find our new salary, we just take the old salary and we multiply it by 1.07. This is the formula. To find the new salary, you take the old and multiply it by this value, the growth factor. And it's growth, it's not decay because we gained. New equals old times growth factor. 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 I said it 5 times. That's how important this is. So the new salary is the old salary times the growth factor. The old salary was the 55,000. I can type, I promise. 55,000 times 1.07. We can pull out our calculator. $55,000 times 1.07 equals 58,850. That should be our new salary, but don't forget to ask yourself, does it make sense? Well, it's higher, so that's good. And 7% is not, say, a massive salary. I mean, it's phenomenal. It's better than, I'm not going to say that. It's better than some people might have ever received in their life, in their current professions. So I'd say that's a phenomenal pay raise, but it's not something absolutely insane. It's not like we went from 55,000 to 100,000. If we got an answer of 100,000, that sounds like we basically doubled our salary, which means we should be closer to like 100% increase. That wouldn't make sense. If we only got, say, like 55,000 and then $850, that wouldn't make sense because that's not 7% of 55,000. And in fact, you can take 7% of 55,000. This is 7% of 55,000. Taking a percentage of something just means to multiply, which is 3850. This is the actual raise amount. I didn't ask you what the raise was, though. I asked you what your new salary was. Now, here's an alternative. If you know the old salary and you know what the raise is, check this out. If you take the old salary and add the raise, you get the new salary, the same value. So that's kind of cool. And there's some math that proves that. It's called factoring, which based on this shouldn't really be a surprise since we're throwing that word around. But I didn't have to break it up this way. I didn't have to take the percent times the base and add to the original. I could. But doing it that way complicates things if you don't have the original and the growth rate. If I had the new, you wouldn't want to do it this way. It's a pain in the butt, trust me. So yes, this makes sense. How would this have not made sense? So I'm going to do this wrong really quickly. Let's say we said that the growth factor, GF for growth factor, was 1 plus 7. Because I took the 1 and then I added the X percent, which was 7. 1 plus 7 is 8. So this is the growth factor, and that says that the new is 55,000 times 8, which is going to be a really big number. It would be $440,000. Does that make sense? No. If you got a 7% raise, you're not going from making 55 grand to $500,000, not in your wildest dreams. So that's showing us that the growth factor was probably wrong. It's saying that this was wrong. All right. So let's flip the script on this. I mentioned earlier, you could be given either the new or the original and asked for solve for either. So this example is a much more common example for our real world. Usually you know your previous salary, and you can be told your growth rate, your pay raise as a percentage, if you will, and then find your new salary based on that. But what if you lost all your old paperwork? You know you now make $71,500, and you just earned a 10% pay raise, but you can't remember what you used to make. You forgot already. So now you're curious, well, what was your old salary? So we just earned a 10% pay raise and we're wondering what our old salary is. This is the number one mistake that people make on this problem. The number one mistake is they say, okay, because we're working backwards, let's call this a minus 10%. No, that is wrong. Because we earned a raise, it doesn't matter if we're moving forward in time or backward in time, this is still a positive value. This is a positive 10%. Whoops, that's not what I meant to hit. Undo. That is still a plus 10%. So let's identify things. Our growth rate, I don't know why I'm using pen. None of this has fancy math. I can type all this. Growth rate is the 10%, which is a decimal, is 0.1. Making our growth factor 1 plus 0.1, which is 1.1. Again, the growth factor just takes 1 and adds the percentage, but as a decimal. What's the meaning of this? Why? This 1 right here that we add counts as 100%. This counts as the original base. So this is saying take the base and add the growth. This is like saying it had the 100% that we originally have plus the new 10%. Again, this is the 100% we originally have, and now we're adding the 10%. If this was decay, we'd have the original 100% and we subtract 10%. So now we're using the equation new equals old times the growth or decay factor. New equals old times the growth or decay factor. But the 71,000 is not the old, it's the new. If you heard that, my chair's creaking. I'm moving some things on my desk. So when we use new equals old times the growth factor, I'm just saying growth because it's not decay. And I wrote gold instead of old. Pay attention, put things in the right place. New is not the unknown, it's the 71,000. 71,500 is equal to the old. The old is the unknown, so we're going to call the old X. That's the unknown. So we get 71,500 equals X times the growth factor, which is the 1.1. Now, 71,500 equals, let's just swap the 1.1 and the X to make it in a more appropriate order. Divide both sides by 1.1. Because this is an algebra equation. We're not just going to multiply the two numbers because they're not on the same side. We have to divide them to solve for X. So we're doing 71,500 divided by 1.1. What's going on? Why is my mouse acting so funny? There we go. I had my pen wrong. 71,500 divided by 1.1. And we get 65,000. And that does make sense. It's less than we make now because we just earned a raise. It's not crazy less. It's not like we went from $10 to $71,000. So check this out. Let's show a couple ways this could have been done wrong. Let's say you just multiply them. 71,500 times 1.1. Oh, let's just do this exactly like the last one and multiply them. You get 78,000 and some change. How would you have made 78,000 in the past, get a 10% raise, and now make 71,000? That doesn't make sense. Now, unfortunately, there is a way to screw this problem up, and you'll think it'll make sense. Check this out, because this is what a lot of students will do. I mentioned earlier that a lot of people say because we're working backwards, they'll call this a minus 10%. So then they'll go 1 minus 0.1, which is 0.9. And then they'll take 0.9 times the 71,000 and some change. So I'm not showing all the work on that because it's wrong. But if you took 71,500 and multiplied it by 0.9, and you might think, oh, okay, well, this should work, 71,500 times 0.9. Okay, well, this is the 10% change. I mean, that seems okay, and this is our old, so you figure if you just multiply, instead of dividing by 1.1, multiplying by 0.9, that's probably the same thing, right? It's actually pretty close, but it's not exactly the same. And this is where people will say, yes, this makes sense. And that sucks because it does make sense. It's in the ballpark of reasonability, but unfortunately, it's not entirely accurate because this is not what you were supposed to do algebraically. This is what you were supposed to do. So you do have to be careful just because an answer makes sense. I mean, that doesn't guarantee, and I've said this before, it doesn't guarantee that it's right. It's just a great way to, if something's very wacky, to know that it's wrong. There are still cases where you can get a sensible answer that's wrong. But at least you can eliminate the crazy, crazy, crazy answers. So yes, there's still ways that a student could mess this up. If they thought this was supposed to be a minus, then they'll get a decay factor of 0.9. If they then just multiply them, which that's 2 mistakes. It takes 2 wrongs to make it feel sensible. Fortunately, most students usually only make 1 of those mistakes, but I have seen plenty of scenarios where the student doubles down on their mistakes. All right, number 4. All right, so here is a scenario none of us want to be in. Also, if you were, I think it was a Centera doctor this semester while all this virus stuff is going on, they took a 10% hit, the doctors took a 10% hit in pay. So it wasn't being scolded, it was just them dealing with, hey, we're out of money, everyone. Fortunately, most doctors make a lot of money and hopefully they're able to, still live off of that 90% pay. But nobody wants to lose money. That's something you don't ever want to do. All right, so you messed up at work. You did something really bad. I have a lot of fun little scenarios I'd love to say in a non-recorded lecture, but we'll just use your imagination and how you could mess up bad enough to deserve a 15% raise. Not bad enough that you get, I said raise there, I meant deduction. Not bad enough that you get fired, or maybe you just are really, really needed. Maybe your company is in a hiring freeze like the state of Virginia right now, so even though you might suck at your job, you get to stay. That kind of thing. So you made $12.50 per hour before. Now, this is a little different. This is a rate. This is not your annual salary. This is your hourly salary. So it was still a rate before. It was just a per year, so we didn't have to change anything. And we still don't really need to change anything here. This is just a different perspective. So they want to say, what is our new rate? Well, first thing you should ask yourself is, should your new salary be bigger or smaller? And I hope your answer is smaller. This is a pay deduction. So you're not going to go from $12.50 to 14 or somewhere in that ballpark. You're probably going to go from $12.50 to like 10 or 11 per hour. So that's one thing to take note of ahead of time. So what do we have? The 15% pay, that's a decay rate, which makes the decay factor one. Oh, sorry, I want to do this as a decimal first. So that's 15%, which as a decimal is 0.15. Making the decay factor, the multiplier. Now it's not 1.15. It's not 1 plus 0.15. It's 1 minus 0.15. Which if you do that subtraction, you should get 0.85. When you have growth, that means you will have more than 100% of what you originally had. So as a decimal, that means you should have 1 point something. Or if you have some crazy insane growth, maybe 2 point something or 3 point something. When you decay, that means you will have less of something. So if you had 100% before, now you should have like 90% or 80% or 70% after of the original. That's why this is less than 1. So new equals old times decay factor. Using that equation again, where the $12.50 per hour, that was the old. So when we plug everything into this equation, we get new equals the 12.5 times 0.85. New is unknown. Call it X if you want it. The old was the $12.50 per hour. And you can include all of your words and units in this if you like, but it's not necessary because the old and the new units have to match. And that's because the decay factor is just a percent as a decimal. So 12.5 times 0.85. We get 10.625. But that answer should be in a specific format because this is a money problem. That's a new hourly rate. That should be rounded to the nearest penny, which is $10.63 per hour. So we went from $12.50 to $10.63 per hour. And I'd say that's about in the ballpark of making sense. It's less, but it's not crazy less. We didn't go from $12.50 an hour to $2 an hour or $5 an hour. We only lost about 15%. So we're in the ballpark, but definitely less. If you got an answer, like I said, of about $14, that would not make sense. Excuse me. Maybe grab something. Okay. So again, not a scenario anyone wants to be in, whether it's because you messed up or because the economy sucks. So we have to fight and just take a hit every now and then. I certainly hope this doesn't happen to teachers, but if it happened to doctors, you never know. I don't know if y'all heard that. My dog is snoring pretty loud. My dogs are funny. I had one more. Yes, I had two more. Good. I didn't used to have number 6. Your salary in 2018 was $52,000. Your salary in 2017 was $38,000. What was the total change in salary? What was the percent change in salary? When you go to take your test, your problems are going to be all over the place. They're not going to go in order, oh, here's the problems from 1.1, here's the problems from 1.2, here's the problems from 1.3, because that's not how things work in the real world. Spoilers, this problem is not what we just did. This is keeping us on our toes. You've got to learn to identify things, write things down as I'm doing, write old, write new, write rates, factors, all that stuff. All right, so what do we have here? Your salary in 2018, 52 grand. Your salary in 2017, 38 grand. Man, that's significant. That to me sounds like someone got a new job. I don't think anyone's getting a pay raise like that typically. Again, typically, especially if you're you know, in a certain profession. All right, so salary in 2018, salary in 2017. I don't see any percents. I don't see any growth or decay rates. I see old and new. So the old value was the 38,000. The new value is the 52,000. We are not asked to find a new value or an old value because we already have them. Why would you ask that question? There they are. What we're instead asked to find is the total change and the percent change. This is what we were doing at the beginning of class. So this has nothing to do with finding growth factors. Ultimately, or with using growth factors. This is about finding them, in fact. The percent change would be the growth factor. So we're going back to total change is new minus old. And then percent change is the relative change. It's the total change divided by the old. Again, we've seen those formulas half a dozen times now. So your total change is the 52K minus the 38K. And if you do that, you get 14,000. That's an increase. We went up from 38 to 52. We gained $14,000 in salary. The percent change would be the total change which we just found of 14,000 divided by the original value, which was the 38,000. I want to put my units in this one. And if you do that division and convert and all that jazz, so $14,000, the dollars cancel out because the same units top and bottom. We get 0.3684, 0.3684, 0.3684, which, when you convert this to a percent, because that's a decimal, is 36.84%, or 36.8, just depending on how you want to round. So that says the total change, again, was a $14,000 increase in salary. The percent change, so this change relative to what we used to make, is a 36%, let's just call it round in the nearest hole, 37% change. Going from 38 to 52 means we just gained 37% more in salary. That is awesome. That is not a normal pay raise. That is a significant promotion or a change in career paths, or your company just extremely outperformed itself in expectations. So everybody's making buku dollars now. So again, you have to be on your toes. You have to look at what you're given and know what to find. When you're given olds and news, you're doing total changes and percent changes. When you're given one of the old or the new and a growth rate or a decay rate, the 15%, that was a decay rate. There's 7%, 10%, these were growth rates. Then you're using the old times the growth factor or decay factor equals the new. All right, this example, and this might not actually be in the notes online. I can't remember if I updated it or not. Sorry for that. So if you haven't seen this, this might be a new problem. You have $100,000 in mutual funds. Mutual funds are a type of retirement account, if you will. It's not, well, I don't want to say it's a type of retirement account. It is a place where you can put your money that is typically associated with retirement accounts, but they don't have to be retirement accounts. You can just invest into stocks and mutual funds without calling it retirement. You can just have it as a, I don't want to call it a savings account, but it's called a brokerage account officially. So mutual funds, we'll get into this in chapter 9, but it's a bundle of stocks. So like, let's say you've got Apple stock, you've got Amazon stock, you've got NVIDIA stock. They make computer chips and graphics cards, things like that. There might be a mutual fund that has all three of those stocks, Apple, Amazon, and NVIDIA. So instead of you just owning Apple, you own all three. You buy a share of this mutual fund and you own a share of all three, basically. Maybe not a whole share of all three, but a portion of a share. So you got $100,000 in retirement. That's what I'm basically trying to say here. On Monday, the market's extremely volatile and you gain 50%. This is absolutely insane. So that means something crazy happened. Maybe this is Hertz, Hertz, that rental car company. They're about to go bankrupt, pretty much. About to means that's what the news articles are saying right now. So because of this, there's a lot of people trying to play that stock. You'll see one day this stock will explode with growth, and then the next day people just do what's called a pump and dump, and they let go of it. So one day it's up 50%, the next day it's down 50%. So your mutual fund, this happens to you, and it usually doesn't happen in mutual funds. So again, we're just having a scenario for fun. So on Monday, you gain 50%. Holy cow, that's insane. And you go, all right, well, do I pull my money now or do I let it ride? And you go, let's let it ride. And on Tuesday, all those people that pumped into the stock are now dumping, which drags the value back down. So on Tuesday, you lose 50%. Are you happy, sad, or indifferent? Most people will instinctively say indifferent because, oh, I gained 50%, I lost 50%, I'm back to normal. That means I got my $100,000. I'm fine. Why do I care? It was nice. On Monday, I had a lot more money, but at least now I still have as much. But is that accurate? Question mark, question mark, question mark. If you gain and lose the same percentages back to back, do you actually have the same amount that you start with? So we got to run through two scenarios. On Monday, we had $100,000 as the old. And the 50%, that's a gain, so it's a growth rate of 50%, which as a decimal is 0.5. Therefore, new would be equal to the old of $100,000 times the growth factor. And instead of going ahead and writing growth factor, I'm going to do it with the parentheses, 1 plus 0.5. If you need to go to the side and write that the growth factor is the 1 plus 0.5, be my guest. I lied, I will write it after this. So that's $100,000 times 1.5. Which is just 50% more than 100,000, which is 150,000. If you do that product. There we go. So here's the thing I said I wasn't going to write originally. That your growth factor, because we have 50% growth, the growth factor is 1.5. 1 plus 0.5. So our new was our original of $100,000 times, now we have 150% of that value. That's what this says. Having a growth factor of 1.5 says that we now have 150% of what we used to. We gained 50% in addition to the 100%, meaning we now have 150%. All right, so that's the end of Monday. But then on Tuesday, now our old value is not 100,000, it's 150,000. When you're dealing with stocks and bonds and mutual funds, you gain that money that day. So now we have $150,000. We gain 50,000 bucks in a day. That's insane. Does that usually happen on 100 grand? No. But if you put your money in Hertz, one day you might have seen this. Actually, one day, a couple weeks ago, they had 100% growth in one day. But then after that, it just crashed, 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 crashed. If you didn't pull your money out that day, woo, you were probably crying. Okay, so our old's 150,000. Now we're losing. We're on the dump cycle. So now instead of a growth factor, that's a decay factor. So our decay rate would be negative 50%, which is negative 0.5. Meaning the growth factor, if you need to see that, or excuse me, decay factor, DF decay factor, would be 1 minus the 0.5, which is 0.5. That's our decay factor. So our new is the old of 150,000 times the decay factor, which is the 1 minus the 0.5. So 150,000 times 0.5. And if you take half of $150,000, you're going to get $75,000. This is the amount of money we have in the end. We started with 100 grand, then we had 150 grand. We were excited, well, we let it roll, and unfortunately, the market crapped out on us, and now we got 75,000. So back to the question at hand. Are we happy, sad, or indifferent? See, I didn't ask you for any of the numbers. I asked you for your mood. And you might say, oh, I've got $75,000. I'm super happy. I'm going to disagree with you. Because, yeah, okay, you got $75,000. That's great. But 2 days ago, you had 100 grand. I'm sad. Me personally, I am sad face. I am sad face because I am now $25,000 under where I was just 2 days ago. So what I love about this problem, there's a homework one related to this, is if you see a gain and a loss of the same percentage back to back, that's actually bad. Most people instinctively think that it balances out when in fact it is bad. And that's because when you gain 50% on 100 grand, you're gaining 50,000. But when you lose 50% on the new value of 150 grand, you're losing 75,000. So you gained 50, then you lost 75, which means you lost more than you gained. Okay, well, what happens if you flip the script? What happens if you have the loss and then the gain? What if you reverse this order? Are you still sad? Are you now happy? Or are you for some reason indifferent? Does this actually have an effect? Does the order that this happens matter? Okay. And just spoiler, see example 10 in text. We're not going to have time for that. What if you reverse the order? So I'm not going to write everything out this time. So now we're going to say Monday, the old is the 100,000. And the decay rate is the 50%, which is 0.5 as a decimal. So the decay factor, 1 minus 0.5, 0.5 is 0.5. So the new is the 100,000 times the 0.5, meaning we only have 50 grand. Yikes. So at the end of Monday, we're down to 50 grand. Right now, you're terrified. Oh no, we just lost $50,000. We were at 100 and now we're down 50. That is awful. Yank the money from the market and just deal with what we have. Believe it or not, that's not my suggestion. But that's what most people do. They lose a ton of money and then they rip their money from the market. But if you actually look at historic stock market records, and maybe not just on a single day, but on a crash like we just had back in March, we lost like 35% of the market in a couple of weeks, if not even that long, maybe over a week and a half, 10 days, 14 days, something like that. But then almost immediately, like 15% flooded back into the market. So someone who lost 35% freaked out, pulled out at the bottom. The very next day, it was up another 15%, and that's 15% that they now aren't going to see. So you freak out and you pull your 50 grand, you might not be too happy because check this out, on the next day, your old amount is now your 50 grand, but we gain 50%. So our growth 8 is 0.5 as a decimal, so the growth factor would be the 1 plus the 0.5, which is 1.5. So our new amount is 50 grand times 1.5. 1.5 of 50 grand is 75 grand. So at the end of Tuesday, we have 75 grand. Okay, is that amazing? What's your opinion, all that jazz from before? Are you happy, sad, or indifferent? Well, I'm a little happy if you just think about Monday to Tuesday because we went from 50 grand to 75 grand. But ultimately, I am still sad. I am equally as sad as the original scenario, in fact, because ultimately I've gone from 100 to 75. But I still didn't pull my money out on Monday, and I'm happy for that because at least I didn't lose 50 grand. I've only lost 25 grand. Maybe on Wednesday this goes up more. Maybe I have to wait a month or a year for this to go back up. But in our economy, things go back up eventually. It might take a month, it might take a year, it might take 2 years, but you do get your money back, historically speaking. Past results do not guarantee future results. This is not financial advice in any way. This is just for educational purposes only. When we get into chapter 9, you'll hear me say that a lot. But the point is, no, it doesn't matter if you gain 50 and then lose 50 if your base value doesn't change. Notice I just said that. If your original value, if you're starting out with 100,000 or 50,000 or 10,000 or $2, whatever it is, if you see a matching gain and loss, you will have less money, and it doesn't matter that the order it happens in, you'll have the same no matter whether it's a gain or a loss. I'm sorry, no matter whether it's a gain then loss or loss then gain. But that is dependent on the starting value being the same. When you're retiring, you're supposed to keep adding money to this pile. Now, when you are adding money to a pile, if you don't start out with 100,000, if one time you got 100,000 and another scenario you got 150,000, that's different. A gain and then a loss would have a different effect than a loss and then a gain because your values are changing over time. And there's not going to be anything about that in this chapter, even the next chapter, but in chapter 9, we'll talk about what you would want to see preferable. What would be better for you if you are continuing to add? Would it be better to have the loss first than the gain or the gain and the loss? And I'll spoil this. You don't want to have the loss last. If you have the loss last, you're going to feel the most significant effect, which is why they tell you when you're in the last 5 years of retirement, you shouldn't be having any risky investments because if the market loses 35%, if you're trying to retire 5 days later, that money's gone. But if you lose for 35% when you're 25 years old, when you're 35 years old, honestly, it doesn't really matter because you're going to have plenty of other opportunity to see gains in the next 20 years of your career. Then when you hit 60 years old, you take that money, you put it mostly in bonds for safekeeping, all these different strategies that you've got hopefully lots of time to learn. Okay, as I said, we're not going to do example 10. Definitely don't have time for that. So let's get into 4.4. And while this section might seem like it's got a lot going on, we're going to trim the fat of it. We're only going to be doing basically what we were just doing, but with some vocabulary that's specific. So again, we're ignoring this for now. It's a fun little problem. Check it out on your own time if you'd like. 4.4, data tables with percentages. We are going to literally do the exact same thing in this section as we were doing in the last section. We are mainly going to be focusing on total change and percent change. Sorry, I'm trying to find out where the formulas are. We are mainly going to be dealing with this stuff again. Total change is the difference of new and old. Percent change is the ratio of total change to the original and then convert it to a percent. Don't forget that last bit. Total change is the difference. Percent change is the ratio of change, total change, to the original. Remember your interchangeable words. Absolute means total. Percent means relative. So back in the last section, we compared 2017 to 2018. We compared apples to oranges. So sometimes the new and the old didn't really have a sense to them. It was just, all right, which one do we call the new? Which one do we call the old? How do we want the numbers to appear? We did an example of that today as well. But again, the data was based on values, apples and oranges, or a dollar value from last year and a dollar value from this year. In 4.4, we're going to be dealing with given values that are percents. So in 4.4, the given values are percents, which means the total change as a unit of percent, but so does percent change. This is confusing. So we need new language. That new language is percentage points. If you're in sports, you may have heard this phrase thrown around a little bit. But percentage points, this symbol PP for percentage points, and there's a couple different ways they abbreviate it, unfortunately, but that's the main one. PPS is the other main one. I was trying to remember what I was commonly seeing, PP or PPS, percentage points. They are used for total change. Percentage points are used for total change. You don't want to have total change being listed as a percent and percent change being listed as a percent. Total change in the past has always been just the number of apples or the number of dollars or the number of people. But now, because we're going to be saying, all right, the thing that happened first was 2% and the thing that happened later is 4%, since those are percentages, the total change is a difference of percents, which is a percent. You can't have one answer be a percent and the other answer be a percent because it's going to be extremely confusing. And that is how the media can confuse you. They'll give a data that says, oh, this is a percent. And then, okay, well, that just means it went from 2 to 4. So it was a 2% increase. That's not actually true. It's 2 percentage point increase if it went from 2 to 4%. Because if you say it's a 2% increase, you're going to have issues later down the line. And we'll see that in the next example, why the language can be confusing. So this symbol, PP or PPS, is only used for total change. When we're talking about the relative change or the percent change, we still just use the old school percent symbol. PP is literally the same thing as percent. They are literally the same thing. On a mathematical sense, those are one and the same. We just use the PP symbol, the abbreviation, instead of a percent to avoid confusion for our readers, for our students, for anyone. Do not ever, do not ever, do not ever list a percent change as a, do not ever, ever, ever list a total change with a percent symbol. Use PP. So this half a dozen times now. Okay. Total change, PP, not the percent symbol. Total change, use PP. Now don't go back to 4.3 and start doing this, because in 4.3, the data given to us were not percents. They were apples, they were oranges, they were salaries, they were people. This is an example of data being given to us as percentages. And you might say, well, this is still talking about pay raises. But instead of giving you, oh, Bob made this many dollars this year and that many dollars next year, or Bob made this many dollars this year and he got this percentage of a pay raise, I have given you a pay raise percentage for last year and a pay raise percentage for this year. I never gave you any of Bob's base salaries. I just said last year he earned a 2% pay raise. This year he earned a 4% pay raise. Thinking that we're at 1 year in the past. 2 years ago, 1 year ago, you get the idea. What was his total change and percent change in pay raise? So because these data values, the things that we're comparing are percentages, the total change must use PP instead of percent to avoid confusion. So the old is the 2%. New is the 4%. He got a 2% increase 2 years ago. He got a 4% increase 1 year ago. These are both increases. They're not base values. So the total change would be the new minus the old, which is 4% minus the 2%, which is in fact 2%. Dot, dot, dot. No. Don't write it as percent. Well, what did we just say 50 times? When we talk about a total change, never use percent. If I do this, it's wrong. I'm supposed to use PP or PPS, 2 percentage points. Again, the S is optional. Either way, it's okay. So he got a 2 percentage point increase in his pay raise. Because 2 years ago, he earned a 2% raise. And then last year, he earned a 4% raise. So the newest raise was 2 percentage points higher than the previous one. That's what this says. It says his pay raise this year was 2 percentage points higher than the previous year. Last year, that means he got 2%, this year 4%. The percent change, this is when we divide the total change and the original. Again, total change divided by original. The total change we just said was 2 percentage points. Weird. What? I've never seen that. Where's my marker? Where did my pen go? That's weird. Remember last class, my marker was acting funny. It's doing it again. Okay, here we go. Here we go. So the total change was the 2 percentage points divided by. That was this. The original was the 2%. Now we said this earlier. The symbol for percent literally means the same thing as percentage points. These are just different symbols to avoid confusion. So when I take a percentage point and divide it by a percent, those units cancel each other out. And 2 divided by 2 is 1. Now be careful, this is not 1%, because the value you get here is a decimal. You have to convert this. Move the decimal right twice and it's 100%. So that's the percent increase in pay raise. So the total change was a 2% pay raise, a 2% increase in pay raise, but we should say percentage points, because the percent change in this, the 2% versus the 4% pay raise, was a 100% increase in pay raise. Can you see how the media could misconstrue this? Oh, look at this company. They gave their employees a 100% increase in pay raise 1 year versus the next year. I mean, yeah, that's true. That's the percent change comparing the pay raises 1 year versus another. But they didn't go from making $50,000 to $100,000. In reality, they earned a 2% pay raise 1 year and a 4% pay raise the next year, which says, okay, yeah, the second year they got a raise that was 2 percentage points higher than the previous year. So as a percent change, that's 100%, because 4 is twice 2. So the percent change here feels extremely significant, but the total change seems minuscule. I mean, yes, it's great that we still made more, but these two values are very, very far from each other. And you can see how media could use one or the other to scare people or to misconstrue information. Total change is just a difference of two things. Percent change is scaled relative to the original. And when you have data that's a percent, if you represent the two percentage points as a percent, all right, the total change is 2%, the percent change is 100%. But the average Joe or Jane is not going to be thinking about whether it's a total change or percent change. They're probably just going to make this the scariest sounding thing, especially if the article is trying to misconstrue it that way. This is why when our data is a percent value, our total change needs to be listed as a percentage points, because when you see this symbol, you know, hey, this was related in just comparing the old and the new as a difference. So I know that, all right, if we had a total change of 2 percentage points, if I got a 10% pay raise the first year, that means the second year I got a 12% pay raise. If my total change was negative 2 percentage points, that means if I earned a 10% pay raise the first year, the second year I earned an 8% pay raise. I still got a pay raise, but it was 2% smaller than the previous year.
All right, so that is going to be it for. Ignore that part. I didn't hit pause in time. All right, so we have one more problem to cover for 4.4, and then we're going to say that we're done with that chapter. We're done with all of the midterm material and everything associated with the midterm. And this is going to be more of a conceptual problem than something you would see on the homework or test, but it's just going in line with what we were just talking about, conceptualizing percents, conceptualizing data, and thinking past just what something says for face value. So that's what this is going to be about. And then we will go right into chapter 5. We'll get into 5.1. We definitely won't finish that section today, but we'll get a good introduction to it.
Drunk drivers are responsible for 33% of motor vehicle deaths. So this was a statistic I pulled up maybe a year and a half ago. So that means if drunk drivers are responsible for 33%, again, roughly, not again, but roughly 1/3 of motor vehicle deaths, that would mean that sober drivers are the cause of 2/3, roughly, or 67% of all motor vehicle deaths. So if drunk drivers are causing 1/3 and sober drivers are causing twice as many, 2/3, why is it that we don't have more news and more worry about our sober drivers? Why do we have so much more focus on, and I don't want to say just drunk driving, let's open this up to intoxicated driving. So not just being intoxicated from alcohol, but any other substances, which we don't need to list. So why is it we focus so much more energy on the intoxicated drivers versus the sober drivers? Now you might say, well, Mr. Beckner, we do put some energy into some of the sober drivers causing issues like texting and driving. That's a very, very common one, or just being on your phone at all in driving. Even with hands-free, there's a lot of theories that say hands-free doesn't really make you much safer. You know, we could throw some percents out there, but they'd be off the top of my head. I didn't come prepared for that today because this is not the whole point. So what are the sober drivers that could be causing issues? Well, the people eating and driving, or having a sip of a beverage that's not alcoholic and driving. Of course, that other scenario would be part of the first problem.
So we have just distracted, just talking to people in the car. If you got a car of 4 or 5 people and you're laughing and having a good old time and music's blaring, you might be paying attention to the road less. So just distracted driving. And then you could say, well, there's also a small portion of people that maybe have an aneurysm or a heart attack or some medical condition while they're driving to cause the accident that could cause a death. So again, the sober, we've got all of those different scenarios, whereas the intoxicated drivers, it's just intoxication through various substances. So again, the point of this question after all that rambling is, why are we not putting more energy? Why do we have so much MADD and sober checkpoints and all this other stuff? There's a lot more energy focused on these people that are causing half as many deaths. The point of this is, it's all about scale. It's all about size of a population doing something. So let's say this red circle, actually we'll do black. Let's say this black, quote, circle, oval, represents all drivers. So this is all drivers on the road. Now I want us to split up this population. Out of the 100% of drivers, I want us to try and think about how many people on the road at any average time would be sober versus intoxicated. Now, yes, it's true that at 2 a.m., this ratio would change. So again, we're thinking on average. We're thinking, 4 p.m., 9 a.m., when most people are on the road. We're not necessarily just exclusively focusing on 2 a.m., 4 a.m. of Independence Day or New Year's Eve or anything like that. So if you just go out at 2 p.m. on a Thursday, most people aren't going to be intoxicated on the road. Yes, there will be some, but most people would not. Now, when I say most, we got to kind of put a number to that. And maybe you're thinking 80%, maybe you're thinking 90%. But even when you lump in all of those people at 2 a.m. and 3 a.m., it turns out to be about 95%. And again, this is a rough statistic, so don't just use this as the gospel. About 95% of the people on the road on average across all 24 hours of the day are what we call sober drivers. And then this other, we'll do it in red, this roughly 5% are the intoxicated drivers. So again, an average on any moment on the road, averaging across all 24-hour blocks. This is roughly saying for every 20 drivers out there, 1 is intoxicated and 19 are sober. Now again, at 4 p.m., the statistic's a little different. At 9 a.m., the statistic's a little different. At 2 a.m., the statistic's a little different. We're just averaging. So the sober drivers here are causing 2/3 of deaths, again, 67%. But the intoxicated drivers, this teeny little chunk is causing 1/3 of deaths. And when you look at it this way, it starts to make a little more sense because we're talking about scale to population size. So this teeny little chunk is causing 1 out of every 3 deaths on the road, whereas it takes this massive chunk just to cause the other 2 out of 3. If we needed to focus a lot more energy on the sober people, it would be a ratio of maybe like 50% are sober and 50% are intoxicated. If that was the ratio of sober to intoxicated people, then first, yes, we would need to put more energy into the sober drivers. And second, we need to start worrying about why half the drivers are intoxicated. That's a big problem. And post-election day, I could make some jokes. Just imagine I made some jokes. But we're talking about life and death, so I don't want to take it too far on the internet. I'm trying to keep it light though. But again, the point of this problem is just blatant statistics. So drunk drivers or intoxicated drivers are causing 1/3 of deaths. Sober drivers are causing 2/3. We need to focus more energy on the sober drivers. They're running rampant. We've got to fix this. This is how statistics get misused in the media. Because yeah, again, while that's true, 1 out of 3 versus 2 out of 3, this is a tiny, tiny, tiny population in comparison to the size of the population causing just twice as many. And again, I'm saying, quote, just twice as many. It takes 1 person to cause 1 death maybe, and then it takes 19 other people to cause 2 deaths, which you could argue that means 17 of those other people aren't even doing anything. All right, so population size, thinking about the dynamics inside of that population, especially if we're talking about one group doing one thing and another group doing another thing. And this is applicable in so many different ways. We can talk about, you know what, I don't want to get into those details because we are behind. But again, there are lots more applications of that concept. Just use your imagination. The one thing I do want to point out that is in the material of this section that I'm not going to test on, however, it is an extremely cool concept that honestly goes along with what we were just discussing, are two-way tables, which are used for data involving 2 specific categories, such as gender or political affiliation, or maybe a drug test, whether you get the actual drug or you get a placebo. You can use this in different testing, like you know, a certain coronavirus, whether you get a positive or negative result and whether it's true or false. And then you can start getting into some light statistics, whereas what's the chance that if you get a positive result that you're actually positive, or if you get a negative result that you're actually negative? Because this is another scenario where when you look at statistics, you look at the numbers and you go, oh, well, that's very obvious. If 95%, yeah, you're good. But in fact, when you start doing the actual probabilities, which again, I try and keep the statistics out of this course, which is why we're not doing it. It turns out that even some of these, like, oh, you're 9 out of 10 fine, even if you get a positive result or whatever, things like that. It turns out that things can go sideways a lot quicker than you would imagine in terms of just the math behind it. It can be misleading is all. So two-way tables, something to check out on your own time if you'd like. I would really love to make to have time on my hands to make a collection of videos for all the things we don't talk about that I could just have linked on YouTube and say, hey, check this out if you're interested. But I'm not ready for that yet. All right, so that is chapter 4. So what we can do now is dive into chapter 5. And I definitely need some spacing here. Let's go. I'll put all this down. There we go. Sorry, I was looking at something. So chapter 5, which will not be on the midterm. Once again, the midterm only covers chapters 1 through 4. Everything from the first day we talked to where I just finished right then and there. That is the midterm, the first 4 chapters. I know it doesn't feel like a midterm because we're into November at this point. It's more like a 3/4 term. Admittedly, this midterm should have been a week ago, but we missed some classes due to random things and rambling and stuff, so let's not ramble more. Chapter 5, proportionality. Well, hold on, Mr. Beckner. Proportionality? Come on. We've been talking about this since chapter 2. We did it in chapter 2. We did it in chapter 3. We did it in chapter 4. So how can you say this is new material? Well, we've been able to make it new material the whole time before this, so I don't think I'm going to have a hard time making new material out of proportionality again. Now what we're going to do is we're going to start studying it in a graphical manner and not always as a proportion. It will, a lot of the times our graphs will be in the same kind of universe as proportionality, but not on the same planet. Sorry, I was trying to think of a way to word that. But when we talk about the idea of proportionality, whether it's actually proportional or just kind of proportional, and we'll get to what makes it kind of proportional later, the graph of something that's proportional or proportional-ish looks like a line. This is a line. Now, some people have the misconception that this is also a line because it just keeps moving and we don't lift our pen. This is not a line. This is what we call a curve. Some people will call that thing on the left a straight line, which is redundant. Calling a straight line is redundant because a line by definition is straight. It's like saying a crooked politician. It's redundant. I'm sorry. I know that's a horrible joke. Oh, the cheese is real. So lines are straight. When you go outside of our course, when you go to the real world and someone says that this thing is a line, you can verbally slap them on the wrist, so to say, and say, no, 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 lines are straight. Now, again, a lot of times when we're talking math in the real world, no one cares about bad lingo and things like that. I was actually just helping someone study for a shipyard exam. We were talking about exponentials and logarithms, and they used the word opposite when they should have used the word inverse. I was like, well, you know, it's kind of slang to say opposite, but the better word is inverse. And then it actually helped them out. So again, real world, somebody might call this a line. Don't be a jerk about it and just go, well, you know, if you want to be technical, it's really a curve, but I don't care if you call it a line because you're not going to affect my life. This is a line. Lines are straight. Now we're going to use something known as the rectangular coordinate system, which has another name, just like a lot of things in the world. It's also known as the Cartesian coordinate system. And this is something that you were supposed to have done in your prereq courses, which I've said about a lot of things, but we don't assume too much. So we give you a quick introduction, but say, all right, if you don't remember how to do this, you need to get to it quick. So a rectangular coordinate system or a Cartesian coordinate system, whichever name you give it, and those are interchangeable, we draw two lines and we label them X and Y. The horizontal has to be labeled X, the vertical has to be labeled Y. And those are what we call our axes. So those are our specifically the x-axis and the y-axis. Where they cross, they meet right here. That's where they cross. We call that the origin. And then what we say is, any location in this flat plane, so if you have a piece of paper, any location on that piece of paper, if you're looking at a wall, any location on that wall, or if you believe that the earth is flat, which is wrong, but if you did, then any location on the earth could be described with a coordinate pair. Now, because it's just a two-dimensional mapping onto a sphere, you can still do the same thing. It's just not technically a rectangular coordinate system, but we're not going to get into all that. So what we're saying is that this point can be described with a pair of numbers. This point can be described with a pair of numbers. This point can be described with a pair of numbers. And we always go the left or right number first, and then the up or down number second. So if I go right, let's say A units, maybe this is 5 or 7 or 3 or whatever, and then I go up B units, this point right here, we would have in parentheses, and it goes A comma B. We go right and then up. That's what I'm trying to describe here. We go right A units and then up B units. Now we could have gone left and down or left and up or right and down. Those are all options as well. It just means that you might have a negative value on the X value or the Y value. The first one is always the X value. The second one is always the Y value. The A was on the X axis, which makes it the X number. The B was on the Y axis, which makes it the Y value. If I swap these two things, it would be wrong. You have to go left or right and then up or down. So something a little more specifically, if I went right 3 and up 1, this point right here would be 3 comma 1, not 1 comma 3. If we went left 3 and then up 1, it would be negative 3 comma 1. If we went let's say left 3 and down 1, 2, 3, 4, 5. This would be negative 3 comma negative 5. Well, Mr. Beckner, what about if you don't move at all? What if you're on the origin, like you said earlier? Well, that point is 0 comma 0. So what I was saying earlier is right here now. How do you plot coordinate pairs? That's what we call the X comma Y or the A comma B or the negative 3 comma 1. It's a coordinate pair. A pair because it's two numbers.
So a coordinate is how we can describe a location. If we're trying to describe something in 3 dimensions, it would be a coordinate triple because you'd need 3 numbers. You need to go how far left to go, how far up to go, and how far in or out to go. So the first value tells you how far left or right. The second value tells you how far up or down. Left is negative, right is positive. Down is negative, up is positive. If you're getting these wrong, practice it. If you're still getting it wrong, practice it more. If you're still getting it wrong, you know what I'm going to say, practice it more. Just because there's only 3 or 4 or 5 homework problems on this does not mean you only need to do 3 or 4 or 5. Some of you are probably good after 1 or 2. Some of you may need 10 or 12. Hit the similar exercise button.
Go to other resources, whatever you have to do, because we will be plotting some lines in this course. We're not going to do a lot of curve plotting by hand, but we will definitely plot some lines by hand. And the types of curves that we plot will not look anything like the one you're seeing over there. They usually look more like this, and we usually let Excel plot those for us. We don't need to get into all the fancy stuff about plotting exponentials. All right. Do I want to go ahead and talk about this?
Yeah, we will.
Look for patterns with larger tables of values. This is going to be relative to the guided exercise we're going to do in just a little bit. When things are on a line, what we're going to really get into is how, let's say you have this point right here, and you know it's what we call rise and run. You can run to the right, and then you can rise to find another point, and then you can run to the right and rise to find another point. And you would be told, or you would figure out how far right and how far up you're going, or how far right and how far down you're going. So you're right and up. And these distances are always the same. And the point is, this pattern continues forever and ever and ever. So instead of just plugging in numbers, processing them algebraically and simplifying to get a number for your output, you could just keep doing this over and over and over and over and over. If you go right 1 and up 5, the next time you'll go right 1 and up 5, and then the next time you'll go right 1 and up 5. So if we're looking at a table of values, to find that pattern, we can look at the table of values. Pay attention to how much the first value is increasing, and then how much the second value increases or decreases. If this remains consistent, you may be able to make quicker conclusions about future data. As I was just saying, you could prevent yourself from having to plug in an X value, do the math, and find the Y value. You might be able to say, oh, well, the next one go up 50, 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 the next one go up 50. But you have to be consistent in one versus the other. If your X value goes up 10 and then it goes up 50 and then it goes up 70, that's not consistent. You would need the X value to keep going up 10 every single time to be able to draw that conclusion about the Y value consistently going up the same every time. And it doesn't have to be 10, it could be 5, it could be 1, it could be a million, it could be whatever number. It just needs to be a pattern. Now, ultimately, I want to go ahead and point this out. You only need 2 points to form a line. All extras are just for checking. If you don't believe me, here are 3 points of a line that I just found. Look, there they are. And if I connect them, if I'm a perfect artist, then these would all go through like so. This one is a little off. Just gonna make them a little bigger, a little more exaggerated. So check this out. If I erase one of these points, so I had 3 to form that line. If I pretend like I never had the middle one, does that change the image of the line? Nope, it doesn't. If I deleted this first point, okay, well, I didn't mean to delete the line too. Sometimes the eraser is a little wacky. There we go. Boom, it's still the exact same line. If I were to erase this third point instead, it's still the exact same line. If I had 4 or 5 or 20 points, this line is still going to look the exact same every single time I add another point because the pattern is consistent. Ignore this difference in sizes of them. I'm just trying to show you a whole bunch of different points. No matter how many of those points I have or keep adding up there, it's not going to change the picture. That is the point of graphing a line, because each one of these points just represents one solution. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 solutions shown here. But what you can visually see in between those is the trillions of solutions. I'm not dashing this, I'm just putting trillions of little dots that are everywhere in between the 1 or 2 or 3 that you found. This is very much saying a picture is worth a trillion, a billion, 1,000, whatever unit words you like. And it shows how the pattern keeps going in either direction. So maybe you got a number for x equals 1 and 3, but your boss says, what happens when x equals a billion? Well, you can use this picture to project that.
All right, so we're going to call it for the day there. So when we come back next time, we will pick up where we left off. We're going to get into a guided activity and we're going to do some graphs, et cetera, but we'll leave that for next time. For now, you know the due dates for everything else, your My Math app homeworks 3.4 up to 4.4, then Excel 4.1 budget. I should have a new Excel file for you to do either next class or a week from today. I'm trying to remember if I'll have it for next class off the top of my head. There's a lot of planning involved with this class and I can't remember. So either Tuesday or Thursday of next week, it'll be assigned. And it'll be from chapter 5, it'll be graphing some lines. The discussion board for week 6, lecture 1 is due on the 6th. You've got your percent quiz also due on the 6th, your midterm. Now, I really, really wish I had paid attention when I was saying this earlier, but I was a little distracted and you might have even heard some inflection in my voice. The 11th and 12th, that's a Sunday-Monday combo. Quite honestly, that wasn't my intention. I was gonna do Monday, Tuesday, which would be the 12th and 13th, but I've announced 11th and 12th. So I'm kind of in between a rock and a hard place as to what to do. I feel a little awkward making you have a test potentially on a Sunday, and if not, you've got Monday. I would much rather do Monday, Tuesday. So I think what I'm going to do is I'm going to send out a poll. I'm going to email this to you. So be on the lookout for this sometime tonight or tomorrow morning. And I'm just going to I'm going to take a vote, and wherever there's more votes, that's what it'll be. So one option will be Sunday the 11th and Monday the 12th. And then the second option would be to take it on Monday the 12th and Tuesday the 13th. So again, this is not something I would ever do normally, but I made a mistake at the beginning of this. And I was like, why did I do that? Why would I ever do that? I'm sitting there thinking about it, what class is going on, and I'm talking to people. And I'm not very happy with myself about that. So like I said, I want to see what y'all think. And if more of y'all would rather have the Sunday and Monday, then that's what we'll do. But I want to make sure that it's comfortable with at least half the class. So again, be on the lookout for this email with a link to just a vote on 2 options, like a doodle. And yeah, like I said, whatever has the higher number of selections, we'll do that pair of days, but I'm not going to make it all 3. So don't think that that's going to be a third option. It's just 2 days, either Sunday and Monday or Monday and Tuesday, the 11th and 12th or the 12th and 13th. So again, I apologize for the confusion. I apologize for throwing all these different dates at you. I just want to make sure that everything works best for y'all. Right. Okay, so don't forget the review. Go ahead and start working on that soon. I will make sure that's available by the end of this evening. And besides that, if you have any questions or if I confused you in any way, please shoot me an email. Besides that, have a good weekend, get lots of work done, stay ahead, start reading chapter 5 materials. I'll make sure those notes to share are available in the Canvas course if I haven't already done so. I think that was the last one that needed to be put in. All right, take care, everybody.